It's stored in 2's complement notation. I'm trying to think which way around that will be.
2's complement.
I don't know if it will be, might be like this.
Is this 2's complement? I thought this would be
That.
sign of magnitude.
2's complement notation, if you want to go back from 2's complement notation, you've got to, am I adding one and inverting, and I'm subtracting one and inverting, I think. Yeah, so subtracting one and inverting would make it
No, it's not
down
subtracting,
to
it's inverting and adding one. No.
that value. That's
So
the
obviously-
subtracting
I've got a
one.
good trick to it.
What I'm doing is I'm going backwards from 2's complement. We haven't covered this yet, we're going to do it in a few minutes anyway. So that's subtracting one, and then inverting the value actually gives you 128. If you're not totally clear about why I'm doing that, don't worry yet. We're going to do signed arithmetic in a few slides anyway. But basically, so the magnitude of a negative jump, the biggest negative jump you can have is 128. The magnitude of the biggest positive jump you can have is 127. So you can jump anywhere in the range, plus 127 to minus 128. So when you have these jump instructions, that label that you put in here, when that's converted to machine code, that will be substituted by an 8-bit value. The 8-bit value will be a signed number.
I still don't know.
So it means that when you do these conditional jumps, the biggest distance you can go from where you are now is about 127, more or less, either way from where you are now in your code. Now you might say, well, I want to do a conditional jump, but I want to go much further than 127 steps away from where I am now. If that was the case, you would have to do a jump to a short step and then do something else, like a long jump or something followed from it. You'd have to do it as a 2-step process. Now you might say, well, what happens if in my label I happen to write some code and where I'm jumping to is further than 128 away? What's going to happen? The answer to that, it will hopefully, if you've got a very good assembler, it will spot the fact that you've done that and it will throw up an error message to warn you you can't do it. If you haven't got a good assembler, it's probably, I don't know what's going to happen. Yeah?
I know, like, the labels are just something that the preprocessor handles and turns into values. Can you? I don't see why you'd ever want to, but can you just? Is it just an 8-bit? Is it just 8-bit?
So you can code up the actual number yourself.
And it's just the address in the code memory.
Yeah. In this case, it would be a relative number. You'd have to work out by hand.
Oh, how the offset?
How many steps to go from where you are now. So you would have to say, well, if I'm on this instruction. The calculation is done from not where you are now, actually, by the way. I'm being slightly dodgy in what I'm saying to you. It's actually, the jump is from where the program counter is now. Remember, the program counter is already pointing at the next instruction. You could, by hand, work out how many bytes that way or that way you need to go, and just code up that value. Absolutely, you could. I don't know anyone who ever does it because it's so easy to get it wrong. And seeing as the assembler does it for you, it's safer to use labels.
Yeah, of course. I was just curious.
Yeah, sure.
Are all conditional short jumps or are they long jumps as well?
There is no conditional long jump. So any kind of, now there are jumps which can be long. All kind of conditional things, which you're doing a test followed by a jump. In the 8051, the condition followed by the jump after that is always short. But like I say, there are ways around it, but you have to kind of do it as a 2-step process. But there are versions of big jumps, but not that do a test beforehand. So unconditional jumps can be long. Conditional jumps are always short. So in fact, now it says there are 2 versions of unconditional long jumps. Actually, there are 3. This slide is not quite correct, which is what I think I said yesterday. I had a doubt about the slide, and I'll prove it to you in a minute. There's long jump, there's short jump, and there's absolute jump, I think. And that's convinced myself. Right, I'm showing you a small bit of the back of the Scott McKenzie book. Now, the reason why I don't recommend this book, although I say it's a good book, and I recommend the Mazadi book for this course,
got that.
is the Mazadi book is a lot about interfacing. This book has very, very little about interfacing. But for the assembly language part of the course, I think it's better written. And there are some copies of this book in the library, not that many though. If you're desperate to get the book, you can always go to Jez Clark and say, I really want the Scott McKenzie book, and he'll get it in, because he's got loads of money now apparently. So don't let that stop you.
Ladies.
Personally, I prefer the second edition of this book. This is the fourth edition I'm showing you now, which has a lot more about C in it, but it's not particularly relevant to this course. Anyway, this is a summary. If I zoom out and show you, I don't expect to read it when I zoom out, by the way. That's, in this one page, it shows you every instruction that the 8051 is capable of, organised as a chart where this is the high nibble and this is the low nibble. So these are all possible opcodes that the 8051 supports. Okay. It actually has a bit more information than that. There's a little key in the bottom. No, you don't need to know any of them. Because, remember, in the exam, all the instruction set is given to you as an appendix. So you get a 4-page appendix in the exam that is just all the instructions of the 8051.
Is it given to us like that, or has it got like a short description of what they do?
I don't know, it doesn't give it to you like this. It gives it to you, the instruction, and I think a very brief description of the instruction.
Okay.
Before the exam, I will show you from a past paper. In fact, you can go to a past paper and you can see what the appendix looks like. If you go to last year's exam paper, which should be available in the library, if you go to the back of the paper, you'll see the appendix. And it will be the same appendix this year. Okay, so for example, if we wanted to increment a direct address, so that's a memory address inside the internal data memory, that would be instruction 05 hexadecimal, because the high nibble is 0, the low nibble is 5. There's a little bar up there, and I'll show you if I move down to the part of the key. Whoops. We can even zoom in for the people who are slightly optically challenged. That little thing there, it says this is a 2-byte operation. Basically, you're going to have to go to the program memory to fetch the operation and the opcode, and then go back to fetch the operand in this case. So there's this key shows you for all the different instructions how many times you have to go back to the program memory to do it, how many machine cycles it takes to execute them. So if we zoomed back all the way over here, I'm going to get a headache in a minute, is right. Oh God. There we go. That particular instruction. It's saying it's a 2-byte instruction, I think.
Yeah.
I can't remember what that key now was.
Yeah, it was 2 bytes. It was 2 bytes.
A 2-byte instruction, but
Zero cycle. Eh?
it's not got a bar down here, so it's actually saying, for however it's able to do it, it's achieving it in 1 machine cycle.
Good times.
I don't know how it's managing to achieve it in 1 machine cycle, but that's what it's claiming.
Magic.
Yeah.
I was going to say, on this chart,
gonna
there's loads
say
of like
thank you.
duplicates. So is it like loads
Because he
of...
goes on.
But not quite
No,
duplicates.
but is it some of the same, but specifically made for each like, register?
What you often find is some of these allow you to, like you'll have an instruction to access a direct memory address, and then there'll be another instruction to access specifically a register. If the direct memory address happens to be one of those registers, you could use either of them, but one of them is likely to take less time to do it. But it only works on part of the direct memory where the register banks are.
So those 2 increments there, that's specifically hardwired for those 2 locations.
That one there, that instruction will only ever work. So that opcode will only ever increment A. And you'll notice it doesn't have a little thing, it says it's only 1 byte. It knows it doesn't have to fetch anything else, whereas this one does. So they are different. Now you could increment the direct memory address where the direct memory address is the accumulator. It's perfectly possible to do that because the accumulator is in the direct memory. But this one, I would imagine, is quicker than this one.
But the compiler will choose the quickest one for you.
If you write in your assembly in K, it will choose that one. If you write inc followed by a direct memory address of A, which happens to be, I think, direct memory address E0, no, it will do that. So no, it won't. It's not going to say, well, actually, although you've asked to do this, I'll give you a better version of it. There's nothing to say you couldn't write an assembler that could do that, but they don't normally do that.
Where would you?
Okay, the reason why I've put this up as well as showing you that is just to prove to you that there is an A jump. Remember that there's L jump.
S jump.
I can't remember what the other one was.
S jump.
There's an S jump. Oh, S jump. Then there's an S jump in here somewhere as well, if I can prove to you. There you go, S jump. So
Wait.
there's 3 versions of jump, not 2. That's all I wanted to show you. So, anyway,
What
let's
about
get
S
back
call?
to the. So this slide is slightly wrong, and one day I'll actually remember to update it. So there is long jump, there is S jump, and there is A jump. And I'll talk briefly about the differences between them. The long jump, basically following from it, you have to give 2 bytes worth of information. There's a 16-bit address of where you want to jump to. And using that version of the instruction, you can jump to anywhere you like in the program memory. Anywhere within the 64K. The short jump basically is followed by a one byte signed number for doing, effectively doing like that relative stuff that we did before. So you can only jump a very short distance. The A jump that isn't shown here allows you to jump anywhere within the same 2K page that the program is currently in. But you can't jump beyond that 2K page. Jumps, these are unconditional. The jump will happen no matter what. Okay? They're not testing anything, they're just going. Now, normally you could write something like long jump to 1, 2, 3, 4 hex. That would actually say go to program memory location 1, 2, 3, 4 hex, and then basically the program will continue running from that location. Effectively, what this instruction is doing is it's overwriting the program counter with this number, and then fetching that instruction. However, when you write your program, I would strongly urge you, generally speaking, not to work out numerically where you want to jump to. Where possible, if you've written a program, if there's some place you want to go to, give that section of the program a label and just jump to the label and let the assembler do the calculations for you. It's usually safer. So if there's a particular place in the code, I'm here now, and I want to get to this place over here, I could just say, and I could just write long jump to go here. When the assembler compiles the code, converts it into machine code, it will substitute the label for the numeric value, but it will do all the calculations for you, which is safer. Well, I don't know, you might be good, but my maths is atrocious, so... Right. We kind of covered this briefly yesterday, but I haven't really said too much about it. This is this idea of subroutines. A subroutine is effectively allowing you to do some kind of jump, but to remember where you were at the time you did the jump, so that when you finished, you can come back to the next instruction that you would have gone to if you hadn't have done the jump. So, if we've got a set of instructions here, and let's say that we're here now, the program counter will be pointing to the next instruction. If this instruction that we're running now happens to be a call, basically what we can do is we can temporarily store what's in the program counter on the stack. As part of the call, oops, I've got my writing dismal today. As part of the call, there's some kind of jump location address. That address can be written into the program counter. and will take us to wherever we want to go. At the end of this thing called a subroutine, the very last instruction has to be an instruction called ret. So the call does a couple of things. It basically says, whatever's in the program counter, stick it on the stack. And then overwrite the program counter with some new information, basically a place I want you to go to. You'll then go there and do whatever you want to do. And then at the end of this little detour, you'll get to the special instruction ret, which will basically say, okay, go back to the stack, take what's in the stack and stick it back in the program counter. Now the program counter, remember, is pointing to the next instruction after the one you just executed. So having gone down here with this, we'll come back here and then carry on running the program here. You don't have to explicitly copy things to and from the stack when using subroutines. It's automatic. That's all the more reason to remember, if you're using subroutines, that you've initialized the stack to be in a part of memory that you're happy for it to be using. So just because you're not explicitly using the stack, don't think that your program isn't using the stack, because it probably is going to if you choose to use any kind of call. There are two versions of call. There's a long call, and I think an absolute call of the two. And here's a very simple program. We'll just do this and then take a break. Showing you how to use a subroutine. So I have no idea what it's doing. So what's it going to do? It's going to toggle the values on port 1 from 55 to AA. Just keep doing that forever. Very unexciting program. But between each time it toggles it, we want it to wait for a little bit before switching it to the next value. And so we're going to change its value here, and then we want to wait for a bit. Then we're going to change its value again, we want to wait for a bit. Then we're going to go back, change its value again, want it to wait for a bit, and keep doing that. Now, we could write this, I want it to wait for a bit twice. I could write out the code here, and I could write out the code here. But whoever wrote this program said, there is a more efficient way of doing this. Seeing as I'm using the same block of code twice, effectively, why not make it a subroutine? So the block of code that deals with the delay has been written just once elsewhere in the memory, and then we're using it more than once. So this is one of the major reasons why we use subroutines, because you might have noticed in the 8051, most of them don't have a huge amount of program memory. And you want to write very efficient machine code that doesn't take up much space. Well, subroutines is a great way to do that, because rather than write the same thing out many times, you're only writing it out once and then just using it as many times as you like. So, it's not explicitly stated where this code starts, which is a bit naughty, but it'd probably be something like org 0000. Okay? If it didn't start at org 000 and we ran this program, who knows what's going to happen, because the processor is always going to start at 000. We're then loading into the accumulator immediately the hexadecimal value 55. And then we're writing that out to port 1. We're then going into the subroutine down here called delay. Now, the program counter, having done this, will already be pointing down to here. So it will be that value that will be stored on the stack. We'll jump down here into here, and we've explicitly made sure that this bit of code is elsewhere, in this case at location 300. And we've written into R5 this number. Now, I think there's a fault in this program. I haven't double checked it, I didn't write it. But I don't think you'd get away with that, and I don't think you'd get away with that. Most assemblers will complain because they'll think that's a label. And it's not a label, it's an immediate address. What there should be here, it should say hash 0AAX. And here, it should say hash 0FFX. Okay? Now, we didn't need to do it in this case because values in the range 0 to 9 can never be a label. So there's no ambiguity there. But in this case, if I was writing this program, I would definitely put those zeros in, and I think actually if you tried compiling it without them, it wouldn't work. It would probably complain. But I haven't actually bothered to test it. Anyway, so we've come down here,
Bollocks.
we've written 0 FF into here. In fact, we've just written FF into R5, and then we're using one of our conditional jumps. So this one is actually taking one away from the register that's mentioned, and then doing and saying, is it now 0? If it's 0, we don't do the jump. If it is 0, we do the jump, which is to go back to here again. So here we go. Take one away from it again. So it's going to go around here 255 times, taking one away from the contents of R5. Eventually, R5 will have the value 0. Then when we do the test, it will say, do a decrement, it's been 1, come down to 0, so you've done the decrement. Is it not 0? No, no, it is 0, so you wouldn't perform the jump, and you'd go to here. And this, ret, basically says, okay, that's the end of this subroutine. Whatever's on the stack will be put back into the program counter. Now, obviously an important thing here is, let's say that your subroutine is fiddling around with the stack. You have to make sure that your subroutine leaves the stack as you found it before you call the ret instruction. If in your subroutine you've stuck some things on the stack and left them there, and then you do the ret instruction, it's going to be a really bad day for you, because you're not going to go back to where you think. You're going to jump to wherever that thing is on the top of the stack. Yeah.
If you never did a call and then you just used return, would it just throw you?
It
to
will
the
go to the
location
stack
instead?
anyway. Yeah, absolutely. So if you don't have the right number of things, it's not going to complain. It will think that there's been something like a call, and go to the stack and do something horrible. Okay, then we come back to here, load into the accumulated new value, write that out to port 1, then go and do the delay again. Yeah.
You know when you can specify where your program is stored
Yes.
in the memory, could you use those locations into the return?
The way this works, with a call, you don't get to put on the stack the value. It's automatically done. Whatever's in the program counter goes on the stack. Now, there are techniques that you can do, and this actually partially answers your question as well. If you want to do some imaginative programming, it is possible to manually put on the stack a couple of values and then issue a return instruction to do effectively a jump. You can do that kind of thing.
Or could you just do a jump to that location anyway and not just do a return?
You could do a jump to that location, but then how would you know where to go back to? Yes, you could manually store it somewhere and go back.
Jump and then return.
Why do it the hard way when there's the easy way? The nice thing about a call is the place where you need to go back to is automatically stored for you.
Yeah.
Now, if you're going somewhere you know you don't want to go back, you wouldn't use a call. You would use a jump.
It's just two ways of doing it.
If you're going to go somewhere to do something and then you want to go back to where you came from,
The return.
the normal thing to do would be to use a subroutine.
Yeah, I mean, like, instead of using like a call and return where it does the stack stuff,
Yeah.
you just put
Now it's going to
back
You
to
could.
ATH.
You could actually do a jump, and then if you know where you need to go back to, you could do a jump back to it. Yes, you could do that. That's possible. Pretty much, in assembly language with 8051, the world's your oyster, so to speak. You can do whatever you like, virtually. And often, there are many, many ways of solving the same problem. And sometimes it's down to programming style, what you like doing. You might say, I absolutely despise long jump, I'm never going to use it. Okay, that's fine. You could probably manage to write any program you want without long jump. There are ways around it. Okay, so we're going to, it's 8 minutes, what was it? 9:58. So 8 minutes past, we're going to carry on. Okay?